Hello everyone. Let's start chapter 1, which is about signals and amplifiers. Let's begin this chapter by explaining what is a signal. A signal contains information about a variety of things in our physical world. For example, information about the weather is contained in a signal to represent air temperature or pressure or any other thing. To extract information from a signal, some processing needs to be done. Usually, processing is performed by electronic systems. But first, the signal must be converted into an electrical signal, that is either voltage or current. This process is accomplished by devices known as transducers. So what is a transducer? Transducer is a device that transforms a physical system into an electrical system. Signal. Okay. Let's assume that a signal is in one of these two forms: Thevenin and Norton. Now we know what is a Thevenin. Thevenin is a voltage source in series with a resistance, whereas the Norton, it's a current source in parallel with a resistance. Okay. Now, if I tell you we have this kind of circuit, we have a voltage source, okay, and we have two resistances in series, and I ask you to find the voltage V output. I need V output in one step. Now there are multiple ways to find V output, but the easiest way is through voltage division. V out which says V output is equal to the voltage source multiplied by the resistance that I am standing on divided by the total resistance R1 plus R2. That's voltage division. Okay, that's voltage division. We will call it voltage division. Now, if I have a current source and two resistances in parallel, R1 and another resistance R2, how can I find the current I? Let's call it IL in one step. Now IL is equivalent, we will use current division. Okay, so current division says the total current multiplied by the resistance that is far from me, for example, so it's R1 divided by the total R1 plus R2. That's current division. Okay, current division. So far we have discussed Thevenin, Norton, how to use voltage division and how to use the current division. Okay, let's go to another page. Now, apparently a signal is a time-varying quantity where the information is represented by changes in magnitude as time progresses. So if we have a y-axis and x-axis, here voltage, on the x-axis time, what is a signal? It's a time-varying quantity. For example, this is a sample of an analog signal. It's just a sketch. Okay, that's an analog signal. So analog signal is a signal that can take any value. If you can see here, it can take any value of a voltage on the y-axis. Its amplitude exhibits a continuous variation over its range of activity. Now, we know that electronic circuits process such signals are called analog circuits. Okay, this is an analog signal. This is an analog signal. Analog signal. But the other form of signal is a digital signal, where it is a sequence of numbers, each number representing the signal magnitude at an instant of time. So how signal can be converted from digital to analog? How signals are converted from analog to digital? First, we mark time instants with equal intervals. So we pick this time, this time, this time, this time at this time instant, this time instant, this time instant. It's just a sketch, okay? Okay, and then we measure the amplitudes, its actual voltage value at those samples. Now this is called sampling. Now the signal is no longer continuous because we picked certain sample point. It's now called discrete time signal. So the discrete time signal looks like this: time, voltage, and at those time instants that we chose, we will draw their values. So this is a discrete time signal. This is a discrete time signal. Discrete time signal. Now it's still not digital. Okay, how does it become a digital? Yeah. So now if we represent the magnitude of each signal sample by a number having a finite number of digits, then it's no longer continuous. It becomes digitized signal. What does that mean? Now you can see here that you have in this discrete time signal, you have samples with different voltages. But if you constrict yourself to a certain values, then it becomes digitized. Okay, so for example, the simplest form of a digital signal is it's binary, 0 and 1. It's 0 and 1. So for example here, let's say 0 and 5 volt, representing 0 and 1. So this is 0, 1. It has only two values, zeros and ones. So this is a digital signal. Okay. Now how do we go from discrete to digital? That's a different story. But I'm explaining in general how to convert from analog to digital signal. I hope now it's clear what's the difference between analog signal and digital signal. Okay. So let's start now with the amplifiers. What are amplifiers? Amplifiers. Amplifiers. In this section, we will introduce the most fundamental signal processing function, which is the signal amplification. We will study the amplifier as a circuit building block, and later we will see the internal design. Now, what is the circuit symbol of the amplifier? This is the circuit symbol of an amplifier. We have an input, we have an output, we have DC power supplies. Okay, so here it's the input and this is the output. Okay, we have V input, we have V output. Okay, on the power supplies, DC power supplies, we have VCC and minus VEE. Let's now move on to the currents. Here, this is the I input, the input current. This is the output current. We have here the ICC current and the IEE current. Okay. We said we will, what's the name of this? It's, both of these are called DC power supplies. Okay. So as its name suggests, the signal on the power supplies are DC, whereas at the input, the signals are AC. What is AC? AC is alternating current. AC is alternating current. Stands for alternating current. And DC stands for direct current. Okay. Okay, let's move on. So what, yeah. Now, one of the equations that we have in amplifiers is the voltage gain. So voltage gain. The symbol of voltage gain is AV, which is equal to the V output, voltage output, divided by the voltage input. Okay, so it's V output divided by V input. What's the unit? It's V over V. That's the first equation. AV is equal to VO divided by V input, voltage gain. Let's move on to the current gain. What is the current gain? Current gain, which is the symbol of the current gain, is AI, which is IO divided by IN. Okay, and the unit of the current gain is A over A. Moving on to the power gain. Power gain is AP, which is equal to P output over P input. Now, if you notice, first, what's the unit of the power gain? It's watt over watt. Now, if you notice, whenever we say the word gain, the actual equation is V output over V input. So whenever I say gain, it's always output divided by input. See, current gain, I output over I input. Power gain, P output over P input. Okay. Now there's another equation for the power gain. Another equation for power gain is AP is equal to AB multiplied by AI. So you can use either this equation or this equation, and the unit is still watt over watt. Okay. Now we can represent the amplifier gains, or we can express them in a logarithmic measure, which is the decibels. How can we express the gains in decibels? Gain in decibels. Now decibels is a unit, and the unit is dB. AV, the voltage gain in decibels, is written as follows: AV which is 20 log the absolute value of the voltage gain, and the unit is decibels. Okay. For the current gain in decibels, it's also 20 log absolute value of the current gain, and the unit is also decibels. Moving on to the power gain in decibels, it's a bit different. It's 10 log the absolute value of AB decibels. Okay. Now, there's one more equation which is for the power of the DC supplies. What is the power of the DC supplies? PDC. It's written as follows: PDC, which is the power of the DC supplies. The power of the DC supplies, we have two DC supplies, right? VCC and VEE. How are we going to find the power there? It's VCC multiplied by ICC, that's one power. The other power is VEE multiplied by IEE. Now we're not going to put the minus. Why? Because if we do put it, the net power will be 0. Now the power of the DC supplies is VCC multiplied by ICC plus VEE multiplied by IEE. The unit of this is watt. Okay. The name of this is the power of the DC supplies. Okay. Another equation is the efficiency. The symbol of efficiency is as follows. The efficiency is P load divided by PDC multiplied by 100. Okay. Now P load is the same as P output. It is P output actually. P load is the same as P output. Okay, and it's represented in percentage with a percent at the end. One more equation is the, let me fix the efficiency. Okay. So the power, another equation is for finding the power dissipated in the amplifier. The power balance equation is as follows. It's PDC plus P input equal to P load plus P dissipated. So in order to find the power loss in the amplifier, you need to check the power that is being inputted into the amplifier and the power that is being outputted from the amplifier. Now the difference between these two values is the power dissipated in the amplifier, which is represented in P dissip, and the unit is also watt. Okay. Now in amplifiers, usually they can ask us to draw the waveform and the transfer characteristic of the behavior of the signals there. Now what is a waveform and what is a transfer characteristic? Let me explain them in general, and then I will give you examples later in details. So a waveform is drawn as follows. It's voltage with respect to time. It's important to put time on the time axis. Now if he asks us to find the output voltage waveform, then we have to put here on the y-axis V output. If they ask us to put or to draw the output current waveform, then we have to put I output on the y-axis. Moving on to the transfer characteristic. It's V output with respect to V input. V output with respect to V input. It's necessary to put V input on the x-axis. Okay. Now, usually in an AC signal, in an AC and a DC signal. Okay, an AC, as we said, is an alternating current. It's not fixed. It keeps changing, alternating. So usually this is a waveform, by the way. See, there's time on the x-axis. So usually it looks like this. This is a sinusoidal wave. How many peaks do we have in this sketch? We have a positive peak and a negative peak. This is a peak and this is also a peak. Okay, the distance between the peak, the positive peak and the negative peak, is called peak to peak. Why am I telling you this? Because sometimes they ask us to find or to sketch, for example, V output is 5-volt peak. So how do we sketch the waveform of this example? We go and write V output on the y-axis, time on the x-axis, and 5 on each peak value, 5 and -5. Okay. Sorry. Okay, this is my signal. So we'll put 5 on the positive peak and -5 on the negative peak. But if they ask us to draw V output, which is equal to 20-volt peak to peak, then we have to do what? We need to put 10 on each peak value, so that the distance between them is 20 minus 10. So the distance between them is 20. Okay, I hope it's clear now. Okay, let's go back to the DC. For the DC signal, it's constant. The voltage has to be constant. It's direct current. Okay. This is the waveform, by the way. I told you this. Moving on, let's take an example on the amplifier. Let's take an example of the amplifier. Okay. So what does this question say? It says, consider an amplifier operating from a ±10-volt power supplies. So let's start drawing this. We have 10. Let's use black, it's better. We have 10 and -10 on the power supplies. Now it says it is fed, focus on fed, with a sinusoidal voltage having 1-volt peak. Now 1-volt peak is the input voltage. How did I know this? Because it said fed. V input is 1-volt peak. Let's continue. And delivers is an output, a sinusoidal voltage output of 9-volt peak. V output is equal to 9-volt peak. Okay, to a 1 kilo ohm load, we have also a load resistance. I told you before that load is equivalent to output. The amplifier draws a current of 9.5 milliampere from each of its 2 power supplies. Now, those are my 2 power supplies, right? So it's saying that the current there is 9.5 milliampere. Let's call it I1, 9.5 milliampere, I2, it's also 9.5 milliampere. Okay. The input current of the amplifier is found to be a sinusoidal input current, sinusoidal with 0.1 milliampere peak. So input current 0.1 milliampere peak. Find the voltage gain, the current gain, power drawn from the DC supplies, power dissipated, and the power efficiency. Okay. I will explain by the way what does sinusoidal mean. Sinusoidal voltage is a sine wave. Okay. We will sketch it in a moment. Let's start with the first requirement, the voltage gain. Voltage gain. Now, as I explained before, the voltage gain is V output over V input, right? Okay. So voltage gain is V output over V input. What is V output? V output is 9 and V input is 1. So the answer is 9 volt over volt. This is the answer for the first requirement. Second requirement is current gain. Current gain. Which is AI. Now, AI is equivalent to IO divided by II. What is I output? I output is here. As you can notice that we do not have the value of I output, but we can find it through Ohm's law, V output divided by the resistance. So I output is equivalent to VO divided by RL. What is V output? V output is 9. And what is the resistance? It's 1 kilo. The answer is 9 milliamps. Okay, let's continue. So I output is 9 milli divided by the input current. What is the input current? It's 0.1 milliampere. 0.1 milliampere. This will give us 90 ampere over ampere. Okay. The third requirement is the power gain, I guess. Yes, it's the power gain. Power gain. Power gain is AP. AP is equal to PO divided by P input. Okay. What is P output? We know that P output is equal to VO multiplied by IO, or we can use PO is equal to VO squared divided by RL, or we can use the third equation, which is I output squared multiplied by RL. Let's use any one of those. I'm going to use V output multiplied by I output. Now what is V output? We know that V output is 9 volt, but it's incorrect to write 9 multiplied by I output, which is 9 milli. Why? Because as I mentioned before, the type of signal on the input and output is AC signal. AC signal means it's varying, whereas on the DC power supplies, it's DC. It's fixed. Okay? Let me sketch the waveform of V input to clarify things. Waveform of V input. It says V input is 1 volt peak, so and its type is sinusoidal. Okay, so we have to sketch a sine wave with 1 volt peak. So this is how it's drawn. Okay, as you can see, the values there are not fixed, they are varying. Okay, so why are we choosing 1? Why are we choosing the peak value? Why not any other value? Okay, let's sketch also the V output. Waveform of V output time V output. The peak value is 9 with -9. Okay, so here why did we choose 9? 9 is only the peak value. It does not represent the entire signal. So a better way to represent the entire signal is to use RMS. What is RMS? RMS is root mean square. Okay, RMS is root mean square. RMS is root mean square. How do we compute the RMS? Now RMS depends on the type of the signal. If my signal is sinusoidal, then the RMS is equal to the V peak divided by root 2. Whereas if my signal type is triangular, then the RMS is equivalent to V peak divided by root 3. And the last type is the square wave. The RMS is equal to V peak. Okay, so this is RMS. So now instead of writing 9 multiplied by 9 milli, we need to write what? The peak value, which is 9 divided by root 2 multiplied by I output 9 milli divided by root 2. Okay, and this will give me, let me calculate it, 9 divided by root 2 multiplied by 9 milli divided by root 2. It will give me 40.5 milli watts. Again, why did I use RMS? I use RMS because the input and the output signals are AC, meaning they are alternating, they are changing. It's inappropriate to take only one value, so we have taken the RMS. You can think of the RMS as if you're taking the average of the signal. Okay, we computed the P output. Let's compute now P input. P input is equal to V input multiplied by I input. V input is 1 volt and I input is 0.1 milli. And as the signals there are AC, we need to also use RMS. So it's 1 divided by root 2 multiplied by 0.1 milli divided by root 2. 1 divided by root 2 multiplied by 0.1 milli divided by root 2 will give me 50 micro watt. Okay, let's plug in the numbers here in the main equation, and this will give me 810 watt over watt. Okay, I hope it's clear. So in general, when do I use RMS? RMS is used only when calculating. I will simplify things for you. RMS is used only when calculating power of input or the power of the output or output. Okay, here we use for the power gain AP is equal to PO over PI. We said before that AP has another equation, which is AV multiplied by AI. What is AV? AV is 9 volt over volt and AI is 90 ampere over ampere. So 9 multiplied by 90 will give me what? The exact same number, 810. Okay. Before we move on to the next requirement, which is the power drawn from the DC supplies, let me compute the gains in decibels. So AV dB is 20 log absolute value of AV. What is AV? AV is 9, right? Okay, so it's 20 log 9, which will give me 19.1 decibels, dB, decibels. Okay, let's compute AI in dB. It's 20 log absolute value of AI, which is equal to 20 log 90, right? 20 log 90, which will give me 39.1 decibels. Moving on to the last, decibels, which is AP in decibels. AP in decibels, it's 10 log the AP, which is equivalent to 10 log 810, right? The number was 810. This will give me 29.1 decibels. Okay, now moving on to the next requirement, we said that it's what? Power across the DC supplies, the PDC. What was the equation of the PDC? The equation was VCC multiplied by ICC plus VEE multiplied by IEE. Do not forget that we're not putting the minus sign. Okay, VCC was 10, ICC was 9.5 milli, VEE is 10, and IEE is also 9.5 milli. So it's 10 multiplied by 9.5 milli plus 10 multiplied by 9.5 milli. This is equal to 190 milliwatt. Now notice here we did not use RMS. Why? Because the power at the DC power supplies is already a one constant value. It's a DC signal. It's not alternating, so we're not going to use RMS. We said RMS is used only when calculating power of input and output. Now the next requirement is the efficiency. I think yes, it's the efficiency. No, sorry, it's the power dissipated, and the last thing is the efficiency. Okay, so how do we calculate the power dissipated? P dissip. We said the equation as PDC plus P input, which is equal to P load plus P dissipated. What is the power at the DC supplies? It's 190 milli, and the power at the input was 50 micro. The power at the load is, which is equivalent to the power at the output, 40.5 milli. 40.5 milli. And the last one is power dissipated. Power dissipated is equal to 190 milli plus 50 micro minus 40.5 milli. This will result in, let me calculate it, 190 milli plus 50 micro minus 40.5 milli. This will result in 150 milli, 150 milliwatt. Okay, the last requirement is the efficiency. Efficiency is equal to P load divided by PDC multiplied by 100. We said that the P load is equivalent to the P output, which is 40.5. 40.5 milli divided by VDC, which is 190 milli, multiplied by 100 will give me 21.3%. Okay, so now we have solved that question. It's easy, simple. You just need practicing. The most trickiest part is when calculating the power input and power output. You need to remember to use RMS. Now let's practice some sketching, how to sketch waveforms and transfer characteristic based on this previous example that I just gave you. Drawings. Let's now practice the drawings. Okay. The question says, the last requirement was number 6, so let me continue to number 7. The question says, draw the output voltage waveform and transfer characteristic. Now note, sometimes transfer characteristic is referred to it as VTC, which is voltage transfer characteristic. Okay, let's start. Now in order to draw the waveform, we said it's V output, because he asked for the output voltage with respect to time. With respect to time. Okay. In order to draw the waveform, you need V output. What is V output? We computed V output to be, if I remember correctly, it was 9 volt. Yes, it was 9 volt. So V output is equal to 9 volt peak. It's simple. We already sketched this before. So we have to draw positive 9 and negative 9 volt. Okay. 9 and minus 9. Okay. Simple. Now, to draw the transfer characteristic, it's V output with respect to V input. V output with respect to V input. In order to draw the VTC, you need to focus on two things. The first thing is the voltage gain, the sign of the voltage gain. Why? I will tell you in a moment. The sign of the voltage gain. The second thing that you need to focus on is the saturation limits. Okay. Now, if you notice now at the V output, on the y-axis it's V output, whereas on the x-axis it's V input. Okay. What is the slope? The slope is y divided by x, which is V output divided by V input. And what is V output divided by V input? Isn't this the voltage gain? That's why one of the things that you need to focus on is the sign of the voltage gain. The sign of the voltage gain. Because if it's positive, you have to draw it like this. Whereas if it's negative, you have to draw it like this. Okay? What was our AV in this example? In the example that we just solved. It was, I think it was 9 volt over volt, right? Yeah, 9 volt over volt. It was 9 volt over volt. So it's positive. It's positive 9. So we have to draw it this direction. What's the second thing? Saturation limits. What is your saturation? The saturation is the actual values of the DC supplies. It's 10 and minus 10. So it's 10 and minus 10. You have to draw a straight line on 10 and minus 10. Okay? 10 and minus 10. What is the at what value of the V input do you reach the saturation limit? We need to figure this out. How do we figure it out? Simple. We say if V output is equal to 10 volt What is V input? We say it's AV equal to VO over V input. AV is 9, V output is 10. We need to figure out V input. V input is 10 divided by 9. 10 over 9. Oh, sorry, this is for minus 10. So here it's 10 over 9. Let's delete this. If V output is minus 10 volt, AV is VO over VI. Okay, 9 minus 10 over V input. V input is minus 10 over 9. Minus 10 over 9. Okay. So we're done with the waveform and VTC. I hope it's clear. I hope you understood this. It's simple. 8. It says if AV is equal to minus 9 V over V. Okay. Sketch the VTC. We said VTC is what? Transfer characteristic, right? Let's start drawing the VTC. VTC, it's V output with respect to V input. Now we said in order to draw the VTC, we need to focus on two things: the sign of the voltage gain and the saturation limits. What's the sign of my voltage gain? It's negative 9. So it will be in this direction, right? Okay. And the saturation limits is the same, 10 and minus 10. 10 minus 10. The x value here is minus 10 over 9, and the value here it's 10 over 9. Okay. Let's draw also the waveform. Here. Let's say and waveform. Waveform, as we mentioned earlier, it's V output with respect to time. Okay. What is V output? What is V output in this question? We need first to know what is V input. Let's say V input is 1 volt. Okay. If V input is 1 volt, how do you calculate V output? We say AV is equal to VO over VI. AV is minus 9, V output is unknown, and VI is 1. Okay. So V output is what? 9 volt. Minus 9 volt, sorry. So how do I sketch this? Notice here it's minus 9 volt. So what should I do with the minus? If you have a minus sign in front of the voltage and you need to sketch it, you have to start from the bottom. You need to start where? From the bottom. Notice here we started from the positive side. Okay. Whereas here when V output became negative, we started from the bottom. This is very important. Okay, we start from the bottom. The peak values are 9 and minus 9. Okay, 9 and minus 9. Let's move on. The next example, what does it say? Or are we done for the question? The next question says, if V output is 12 volt, sketch the VTC. Let's say sketch the waveform and VTC. Output waveform, and VTC. Given that AV is 9. given that AV is 9 volt over volt. Okay, let's start with the waveform. In order to draw the waveform, what do we need? We need the output. What is the output? It's 12. Now, in order to draw the waveform, you need to check, did the value of the output exceed the saturation limit? What is our saturation? Our saturation limits is 10 and minus 10. And here our V output is what? It's 12. Okay, so it has exceeded my saturation limits. So what do you need to do? First, my expected output is 12 and minus 12, right? 12 and minus 12. This is my expected output. But what is the actual output? The actual output is 10 because of the saturation limits. So you have to crop the signal at the 10, okay? And then just trace it. So that's how it will look. Let's do the VTC now. Let's draw the VTC. VTC is V output with respect to V input, okay? Now, as I said before, in order to draw the VTC, you need to focus on two things. The sign of the voltage gain and the saturation limits. In this question, what's the sign of my voltage gain? It's positive 9. It's positive 9, see? Positive 9. So, it will be, sorry. It will be in this direction. I don't know why is the line squiggling. Anyhow, it's just a sketch, okay? And what's my saturation limits? The saturation limits is still 10 and minus 10. It did not change. And the X values, we computed this earlier. It's 10 over 9 and minus 10 over 9. Okay? Okay, so we're done for this question. Let's move on. So far, we have discussed the amplifier. From the outside. We have discussed the amplifier as a symbol, circuit symbol. Now what are we going to do? Now we're going to dig inside. We're now going to dig inside the amplifier. Let's figure out, or let's investigate what's inside the amplifier.